That's nice to have an usually very well.
I can't even tell someone else where it is. Yeah, sorry. That's okay.
See if you can.
Doesn't project.
No, I can't do it. Replicate this signature tab.
There's no chance. I just.
That is literally my signature. Gotta do it faster than that.
Oh. So, who we are, what are we doing? So it is a physical chemistry class. We want to predict outcomes of measurements for some instruments, materials characterization, and we are getting through laws of wavy motion of electrons in atoms and molecules. We've got most of the basic principles and laws, and we are trying to apply it to the simplest possible problem, one-dimensional electron without any attractive nuclei. And our hypothetical predictions before we start doing calculations were that the center of the initially localized wave packet will either stay still or move with constant velocity, and the shape will expand. And we kind of get to this expansion stage last time, but it was a little warped, and I'm not sure if you left any positive memories or take-home messages. So I'll probably go over once again. And the new part today will be related to. Thank you so much. This class is much more organized than in previous years. Before it was a headache. Everyone selected like 2 or 3 options. I can do this and that, and I needed to administer, and it was very dispersed through the material. Thank you for making ready to present with. We got a result about expansion of the width and projected it towards so-called uncertainty principle. The position of momentum cannot be measured simultaneously. But in the little exercise that we processed through homework and our class exercise, the center of the wave packet was not moving. It is possible, and I can show how to do it just by pointing place in the equation, but getting the linear motion of the wave packet through standard third way of predicting future through expansion over wave functions is possible, but a little torturing. We already see that all these integrations are possible, but they are a substantial waste of our time that we can spend doing sport or going to the party. So there is a like in shop for like repairing something, there are specific tools and instruments for each task. And if you want to look at the motion of the center of the wave packet, there is much better tool. This tool that we will introduce on coming Friday will be maybe 4th way to predict future. And to apply this 4th way to predict future will be really quick and easy. Maybe like 5 or 10 times quicker than this Schrödinger expansion. But the principle where this 4th way is coming from is a little non-orthodox. One needs to wrap mind around new concepts. So we will go over completed stuff. Once again, I'll try to be a little more organized if possible. And then we'll start preparation of things towards 4th way to predict future. Oh, yeah, and I know we all are trying to invest time in homeworks, which is I'm not sure about this date, but let's tentatively planning to come Monday. So I do not see big protests. So for the first one, for the figure communication, it's 1 minute. This is just copied from lecture notes. This is also not challenging. You do not need to take integrals because they all are taken. One needs just take integral of this stuff, make it equal to 1, then divide. Take 1 over the result will be this n constant. And I'll go over it. This one I also copied from the lecture notes. And so everything except question number 5 is really easy to take 25 minutes. And this number 5 will be like half an hour. If you are taking differential equations, it will be quite major before you solve the problem. So matching the function to the boundary conditions. And I'll probably go over it once again on Friday before the lecture so that we have a little guidance. It doesn't look scary. The number 6, if you do number 6, you will get more than 100%. Or if you're not sure about one of the obligatory parts, you just do extra credit and get extra points to cover anything missed. So it is basically math rather than physical chemistry. Just find a way to take this integral. It will be used in the class maybe 2 weeks later. So we already filled this table and relax, going back, take a nap. I'll give you warning when it will be something really important. But now it is just repetition of what we did in the previous 2 lectures. So we predict future by expanding, by adding together or integrating the eigenfunctions with phase accumulation in the power of exponential, and these terms are weighted by expansion coefficients, which you successfully computed in your homework. So to be able to take this integral, everything that stands in front of second power of the integration variable will be put together in one constant. Everything that stands in front of the linear into another constant, and then one takes take this integral. So it will be taken easier if one redefines new variable. So if one instead of k, one introduces new variable connected to this linear transformation, then increment will be connected by a factor, and the integral. So I need to focus. Not because I like to see myself, but it's anyone wants recording its paper. And here is just integral e to the power minus y squared. So after this substitution, here will be the integral that needs to be taken from minus to plus infinity, and the price for making the substitution is in the factors, one of which is a square root and another is exponential in powers of this stuff that we defined before. And since integration of this e minus independent variable will be square root of pi. Always forget pi. The answer essentially will be depending only on plugging in these two variables into this exponential. And if you look on them cold-blooded, it will include both spatial variable and time variable. Something will be changing both in space and time. Nothing new, nothing the same. So we have definition of this uppercase P, uppercase A. We plug them into here, and the result will include position squared in the numerator of the exponential power, and in the denominator there will be initial width and some time-dependent factor. So the keep sleeping, keep your nap. It's not important. It was already in previous time. And here is let me write it down. So wave function is only an auxiliary tool. The things that we can analyze and use to predict future are probability distribution, which is a little more useful, and observables. Right now, we are focusing on probability distribution. Starting from the last 10 minutes of today's lecture and Friday, we will be more focusing on observables. So for probability distribution, one needs to take absolute value of wave function squared, right? Or wave function times start times itself. It will be probability distribution. And this is the stuff that we need to explore. So if we want to make this construction out of this wave function, we just need to multiply it on itself, but upon conjugation, one swaps the sign in front of imaginary unit. So one exponential is I, one exponential is minus I. Product of exponentials corresponds to one exponential with summation of their powers, right? And if we need to add together two fractions, what is the rule from middle school, high school algebra? Yes, one needs to build a common denominator. So multiply this factor by this denominator in left and right, and multiply this top and bottom on this denominator, right? So here is the product of the two denominators, right? One is plus I, another is minus I. And on the top, it will be x squared and then summation of this denominator. So it's plus I and this minus I.
For the original electric, is it plus or minus for the I?
I think.
Like which one's the
I do not want to lie, I don't remember. If you tell it for certain, it will be extra credit. And here there is another error that I caught myself. One of these i's should be plus, right? so that time-dependent stuff in the numerator cancel, and in the denominator, first term is the same, second term is the same with difference only in minus sign. So this x plus y, x minus y, x squared minus y squared. So we will have sigma naught squared divided by 4 minus all this stuff squared. So imaginary unit squared will be minus. And then we get rid of imaginary unit. And it will be 1 minus from this algebraic equation, and another one from square of the imaginary unit. So it will be initial width plus quadratically raising term. Okay. And again, it's hidden by this little stuff. So here is x squared so this probability distribution. And if you want to analyze this equation, then it looks like a Gaussian function centered at 0, where the width depends on that. At initial time, there is some certain value that we agree on, each of them, and it is not a cross product. We just highlight that it's multiplication. So, and then as time passes by, the width of the wave packet quadratically grows. So it becomes fatter, more expanded in space. And we already discussed this part last time. This is the observation that we do here in class, but there are serious consequences from this little calculation. It follows that position and momentum cannot be measured simultaneously. There is a so-called uncertainty relations. Product of the uncertainty of position and product of the uncertainty for momentum is equal to the constant or bigger than this constant. So in momentum space, the width doesn't change this time. It's constant. And if one sets up product of these two width parameters, their product will be equal to constant plus quadratically growing term. So in original formulation of the uncertainty principle, it doesn't tell about this plus term. It just tells sigma x times sigma p bigger or equal than one constant square. And since it grows, it's clear that it is bigger. Interestingly, if you put time negative, it still will be growing. So there is one question maybe somewhere formulated in the homework. Is it possible to make the wave packet narrower than minimal width? And it is not a certain question for given immediate answer. It's just for your thinking and common sense thoughts. Okay. Uncertainty principle. So we are done with last lecture and start a new one. So here is a little stuff that we are going to get into in whatever 10-15 minutes. If you're comfortable with it, you can just pack your stuff until you have some other things to do, or you can just start reading news on your equipment. So the first line should be familiar to everyone, right? Time-dependent Schrödinger equation. The little dagger here means Hermitian conjugation. And Hermitian conjugation means that one, if it is a square matrix, one swaps it along main diagonal, changes rows and columns. In addition, if there were any imaginary elements, they must swap the sign. So Hermitian conjugation is transposing of the matrix, which means changing rows and columns, and simultaneously swap sign in front of any imaginary unit. So complex conjugation and transposing, if you talk about matrices. So there will be necessity, there will be motivation that I'm not right away, I will present in details. There will be necessity to do Hermitian conjugation of overall Schrödinger equation and each of its element for the following purpose: for predicting outcomes of measurements. So if you want just future in general, it's good, it's enough to have wave function. But if you need specific outcome on measurement with the instrument, we need an observer. And for predicting outcome of an observable and future of the measurement, what will be the measurement if one would do it next year or next femtosecond? One would benefit from applying this Hermitian conjugation to the Schrödinger equation and each of its elements. So after applying this conjugation, the left part becomes complex conjugate. If you were dealing with wave function as in matrix form, instead of being column, it will become a row vector. And here there is a very strange thing that do not try to think about it from common sense. It's all mathematically correct, but it's not healthy to think too much. So operator acts, typical operator acts from left to the right. If you do this operation, the operator starts acting from right to the left. And I'm not going to prove, but I will show that it makes sense. I will give some arguments. And it will be conjugated wave function. So if you're comfortable with this statement, then the rest will be just entertaining. Who presented this formula? Okay, so if I explain it insufficiently, ask Alisa. She is So this is a general prescription of how to obtain outcome of a measurement. Of course, any prescription has limitations and ranges of applicability, but it is a very good and useful formula. It is a bridge between abstract way of this mathematical theories and what one is getting in actual experiments. So instead of operator A, one plugs in operator that is constructed according to a little chart. It was distributed a couple of weeks ago, right? Differential operators. And to the there should be dx here. And at the left and right of the wave function, one plugs in the future that we have already predicted, right? Wave function. And in some sense, you can start your independent research career right now, without any new independent research careers as physical chemists, as theorists right now. Anything that will be after this instant will be just combination of previous materials and some mathematical tricks. You can already predict outcome of any experiment if you build operator of the measurement, observable, and if you predict wave function as we did before. Nothing is wrong with this approach. And especially if we live today with everything is computerized, it's a perfect approach. When resources are cheap, you just plug in a way to numerically solve Schrödinger equation, and then combine your predicted wave function with operator of observable and predict outcome of an experiment. But what if our wave function is more than one dimensional? What is if much more dimensions? What if we live 50 years ago and we are not so computerized? If you want to save effort and resources. So here is this thought that you may wake up and concentrate on it a little. Wave function, if you save it numerically on a computer, it has a lot of data, a lot of grid points, and at each point of time. So it's a lot of data progressing forward. If you need an observable, it is either one number if it is single measurement, or a function of time if you look how it is changing in time. So this observable, this set of data has much less weight. It is much easier to store and deal with. And it is the only valuable thing that we can sell outside of this class. If you want to come to someone who is doing NMR or spectroscopy, they will need just observables. They do not care about wave functions. Right? So a lot of this wave function information is waste of resources. What if we have a magic tool to predict the outcome of measurement right away? Just get rid of wave function at all. It will be cool, right? I think it is enough intrigue and motivation. And we will go over this new method, and I'm keeping intrigue and do not give the name of the method, but it will be a forced way to predict future in sense of observables. Not all future, but only for specific observable, and we will apply it to position of the wave packet if it started with initial velocity. So the solution, we will be speaking for like more than an hour, and solution will be in 1 minute. Okay? So if you look onto this equation, we do see conjugated wave function. And if you already have solution for wave function, we just make conjugation numerically, or if there is an equation, we just swap I to minus I, change the row to the column, and that's it. But what if we do not have the solution yet, and we want to make some conclusions? So it's a traditional way of thinking for mathematicians, to develop some conclusions about object without having object in hands. So theorize about object without having it. Then we need to write down an equation of motion for the conjugated wave function, okay? And make some conclusions and observations how it will look like. An analog of Schrödinger equation for conjugated wave function. Oh, we already discussed it. Hermitian conjugation is swap of I to minus I and transpose. Diagonal elements stay the same, and off diagonal swap. Right? What was a row becomes a column. What was a column becomes a row. Right? I have something same idea type. Somewhere. Yeah, this is if you keep your net, something important. So if you have a general matrix where each element has a real and imaginary part, like here's A11, B11, B1, 2, and we apply this dagger, which is symbol for Hermitian conjugation, then we swap the sign in front of imaginary unit everywhere, and we swap place of the off-diagonal element. Good? I didn't introduce anything new, we discussed. But if suppose that your matrix is diagonal, so there are no off-diagonal elements. Suppose that your matrix is real, there are no imaginary values. Then what will be the Hermitian conjugation of this matrix? So diagonal elements stay the same because so if imaginary part is 0, then here we have A11, A22. Zeros on the off diagonal, no imaginary elements, and you'll be on the main diagonal A11, A22. So for real diagonal matrix, Hermitian conjugation reproduce matrix itself. Okay? And neither you nor me are mathematicians. This class is not math, but there is a definition of Hermitian matrices, which remain itself upon Hermitian conjugation. Why it is important for physical chemistry and quantum theory? Because there are thoughts and theorems that good Hamiltonian in good problem is always Hermitian. So Hermitian conjugation of Hamiltonian gives Hamiltonian itself. Do not focus too much. We will just use this fact for one of the next derivations or the next demonstrations. And I have the same, do not look here, I have the same stuff in a better visualized form. Okay, I'll tell anyway. So if you have a row and column, applying Hermitian conjugation to a column, it makes row. And if one applies Hermitian conjugation to matrix multiplication by a column vector, so if one writes down row by column rule by elements, then apply conjugation, one can prove that it will be equivalent to counterpart of this vector changed in the row form and Hermitian conjugation of the operator. So why do we need it? In order to find observable, we need wave function and wave function conjugated. We already know how to predict future for conjugated, for actual wave function. Now we need to predict future for conjugated wave function. In Schrödinger equation, we have time derivative and wave function on the left part. Application of conjugation to time derivative will not change anything because it doesn't have imaginary thing. On the right part, we have Hamiltonian that acts on a wave function. So let's just observe what will happen if we apply this Hermitian conjugation. So I'm skipping a proof here, but there is a proof that before conjugation, Hamiltonian acts from left to right. After conjugation, it is Hermitian conjugation of Hamiltonian, but it is equal to itself. So you can write just Hamiltonian. And now it acts from right to left, if we do it as differential operators. If we swap from differential form to matrix form, you just multiply matrices by row by column row. I'm proud of this picture. I spent all my morning of drawing these pictures. So, if Hamiltonian is a square matrix and wave function is a column vector, you can draw them this way. After making conjugation, wave function becomes conjugated, which means it will be a row vector, and Hamiltonian will stay the square matrix. Right now, I'm skipping because of saving your time and practicing laziness myself. I'm not writing element by element. But if you spend your time looking for textbooks in physical chemistry, highly likely you will find such example, where one writes carefully all elements. So we have still row by column. Here is matrix times column. Here is row vector times matrix. Same stuff, just this. So once again, if we do have the complete thing, Schrödinger equation, take derivative, wave function, Hamiltonian wave function, apply Hermitian conjugation. My favorite form. Square boxes. So apply Hermitian conjugation, then the column wave function changes into a row wave function. Column wave function changes into row wave function. And order of wave function and operator, Hamiltonian swap. So what is written here is an equation of motion of conjugated wave function. It is what we actually need for exploring observables. We are not going to do it today because there are like a couple of minutes left. But it will be a building block on which it's a foundation on which we will build our next video, next lecture. We need Schrödinger equation. We need equation that predicts future for both wave function and its conjugated counterpart. And if we remove the boxes, we'll have just equation that we started with, the summary of today's meeting. So operator acts from right to the left. Thank you for your attention and dedication to the class. We are done. Looking forward to see you this evening. If the tech support emailed me that they made an effort to install MATLAB, but if you bring your personal equipment and make an effort to install MATLAB personally, university provides license for anyone that you benefit. So it's, and you may spend, because your schedules are likely busy, you may spend time in the lab for exploring this option. Okay.
When is the homework due again?
Huh?
When is the homework due again?
Monday?
Monday? Okay.
Do you know how long the lab will go to?
Do you need to look earlier? As soon as you know which subject you present, if you are silly, you can just check if there will be a part of what you need to present today. And if it is something else, you can wait.
Thank you.
Hoping that your classmates will teach you during the presentation.
Alright, so you guys.